All right, so let us continue. It's a great honor to introduce to you Professor Moira from Stony Brook. The next speaker from Lefschetz to String Topology. Please, ma'am.
Hello? Working the thingy?
Yes.
So hi, sorry you're stopping me again. And I mean, when I was really preparing this talk, I realized that it was incredibly ambitious. So I don't think I'm going to talk about string topology or Lefschetz, the view. And so let me start. So let's start with the surface with boundary, orientable. So here we have a pair of pants of with here with 3 volts. This is the pants of somebody who has a very strange body that we are ready to see here, so fine. The goal is to study curves on this surface, curves up to free homotopy of deformation. So to do that, we're going to cut the surface, and the cuts have the rule that you can go from boundary component to boundary component. They don't intersect, and they don't intersect each other. Here I have 2 possible cuts, and you put the maximum number of cuts with that property. So on the surface, when you open up, you have a polygon. So here it is, and I keep a memory of the cuts. So here I have colors and also letters, that is set of memory, and the letters, they have lowercase and capital case, and will play a role in a second. The point of this is that now if I forget my picture and I know the recipe of how to construct the surface, if I give you the edges, really in a secret word, it's a secret word, it's a circle of letters, then I can reconstruct the surface. So the topology of my surface is encoded there. So here I have, for instance, a torus with one boundary component, and I claim the surface word is AB, capital A, capital B, capital. You have to read it as A inverse, A with a bar. I program many of these things. You don't put an A bar, in the program, so capital means that. So here we have a torus with a boundary component. So here I have 2 surfaces, different surfaces. I need the same alphabet to encode both, but as you see, they have different words. The pant has AABB, and the torus is ABAB with appropriate capitals. And the surface words know how the curve intersect, and then I'm going to tell you what they know about it. So now we're going to look at curves. So now we're going to fix the surface and a way of cutting it. And here I have ways of labeling curves up to the formation of free homotopy. So here, just point. Well, let me see. I have a way of pointing. So for instance, I want to see which word, can you see my mouse? Yeah. I want to see which word it labels the curve that I have here, where my mouse is sitting. I start anywhere. There's no base point here. This is just the image of a circle oriented. So I start here and I cross the edge labeled by a small a. So I'm going to record the small a. I know, because we are all so smart, that after a small a, there's always come an a capital. So I'm not recording the a capital. So small a, and then go around, big B, go around, capital A. Oh, I'm going in the opposite direction of my arrow. Apologies. Well, anyway, let's do it. So this will work. This will be the other one, which is, if I follow the sense, is it should be, I lost it. Well, here I wrote A, B, but it should be small b, small a, capital B, capital A, if you run it with the side value, which is the opposite that it says there. The point is, every time I cross an edge, I record the letter that I see before I cross it. And so that gives us a curve word. So these are 2, they are objects that are writing the same letter, but they have a different purpose and different rules. I can repeat letters in a curve word. The surface word has, every letter in inverse exactly once. And of course, are reduced because having a letter and a letter bar next to each other means it's going back and forth and we're working out the homotopy. So to label things, we always use reduced words. And then now what we want is to study the number of crosses of this class using the curve words. So here I have a complicated curve. And now you see why it's nice to be able to cut the surface into a polygon. You can see the intersections much better there. So I'm looking at this curve, and here, this is the curve word. For instance, there's three A's, there's three little A's together, which, here we have these three crossing. You start here, you go to this edge, come here, you go to this edge, come here, back here, and so on. And but from now on, I'm going to write the letters, the curve words as a linear word, because it's very painful to be organizing the letters, in a circle, but your imagination should put it in a circle. And before I continue, I told you a general purpose for the next half an hour, which is we're going to look at three homotopy classes of closed curves. So let's missing there on the surface. Well, often with boundary, but many things work for both. And there's many ways of looking at it. We can look at the simply produced word, this thing I just described. It's a controversy class of the fundamental group of the surface. And also, if we have a matrix, and all my metrics are constant negative curvature, you can think of the geodesic in the class of the curve. There's three incarnations of my class. So I can associate three numbers to this the three homotopy class. One is the number of crosses. These are the number of, we can think of the transversal double crosses and minimal. So you homotopy occurs, so it crosses itself the smallest number of times. And it has the word length. So here, when I fix, I have to fix a generator, which is of the fundamental rule, which is equivalent to, choosing these cuts. So then you have another integer, the number of letters that the word associated with the class have. There's a geometric length, and again, here we need, and my metrics are always constant negative curvature, and so these are three numbers. I'm interested in relations, statistics, patterns with these three numbers. And the small word thing, I use a lot the computer. So my collaborator, I have human collaborators too. And I probably want to mention the Goldman Lie algebra, which is an algebra that is related to, the terms are computed using the intersection and self-intersections of curves, and the number of terms know things about how the curves cross each other and themselves. Okay, so now I'm going to compute the self-intersection number. I will go back to our complicated curve. And there you see, I highlighted two pieces of curve containing a light blue self-intersection point. And, I want to relate this intersection to the word. And you see, this intersection is there because there's two segments of the curve, two pieces of the curve that cross like this. So one goes to one piece of the curve, goes to the segment, goes to this edge, the cut labeled by small b, to the cut labeled by big B. And the other one goes to the big A to small a. Now, why do I have the segment, the vertical one from B to B? Well, because my word contains the sequence capital B, capital B. Every time the other word, no matter how long it is or short, but it contains B and B, one next to each other, you will have a segment going from top to bottom. Same thing with the horizontal inch, from AA. This AA going from A to A is one of the occurrences. Since I have three small A's, I have two occurrences of two consecutive A's. So anyway, every time I have a BB, I have this, and every time I have an AA, I have this, and then we have an intersection. If you want to remember something, this is a good picture to remember. Not all intersections can be found this way, but this is the essence of how they are found. So here it is. I marked this is the same word, and I just highlighted the two subwords that yield that self-intersection. And then I repeat, anytime I have these pairs of subwords in a word, I will have an intersection of the corresponding curve. And of course, since the world, has to be more complicated always, there are more complicated intersections. If I look at these red segments that contain an intersection point, you see they are both born on the same vertical edge, this vertical cut. So a priori, when you see a word small a, small a, small a, small a, small a, small a, small b, one doesn't know whether it's an intersection or not. It could be like this and could be like this. But to know whether they are cross or not, we have to look at the paths of this curve, where they came from. And I put it there in the same picture. Maybe I point, so the segment that, from here, it's coming from the big B, and it's coming from the other coming from the big A. So what I know is the curve does, is born like this. They go to the same segment. Well, in this particular case, they do like this. So I'm going to have an intersection. But in general, you can have a piece of curve that starts in two different paths. And then they go to the same, and then they can go together for a million, letters or cuts. And then at the very end is where you have to study. They are right here, whether they cross like this or they cross like this. So if they cross like this, no intersection. If they do this, and this is just the beginning and the end. The three, the three letters at the beginning, the three letters at the end. This is something that you can put in a computer because it's, the relative semicolons will tell you whether there's a crossing or not. So there it is. These are the three types of, I call them link pairs. They have a few names in literature. And one thing that is essential, they can go in different directions, but still do this thing. And these are basically all the intersections. So here is the theorem that unfortunately I didn't prove. I thought I did. I was very happy, but in fact, first, Riemann series, they show they use this word form to study when a curve is simple. And then Lustig, they push that forward, the same idea to, show intersections. And my form is an equivalent from their algorithm, but basically says that, so if you have a curve that intersects in the minimal number of points, and just for ease of mind, is transversal double point, it's a one-to-one correspondence between certain pairs of subwords of the word. So there's a list that is given by the surface word in the infinite list, and how many of these pairs occur in your word will tell you the self-intersection number of the class. Any question? Amazing. Einstein? No? Okay. So all of this is something you can put in a computer. So I put it in a computer. I don't do anything that I can, but this was a good idea, so I did. And I made a table, and it was just playing around. So in this table, it's a spreadsheet. For instance, here in the column 1 and row 2, I counted how many classes or homotopy classes of word I have that can be represented with the 2 letters. So the row gives me how many letters, and the column gives me the self-intersection number. So here I have, this is in the torus, country torus. So here I have some examples just for us to see. So for instance, no crossings and 1 letter, well, the 4 generators, and so on. And here, well, the computer can do it. More counting, and here is even more counting. And when you compute here, when I compute this, I start to feel happy, because you start to see a pattern. When we see patterns, I think we most of us say, this is nice, let's prove it. Now, by the way, I didn't say this. The previous slide, when I look at the words, I always look at classes that are not proper powers of another classes. I don't want to go twice around. And what here is a little bit of the reason why. Look at what happens. Here I use my pattern. My table is all, but the green, you cannot see. The green is when you have no curves. So after a subset of intersections, you have no curve. But if you allow powers, you get this island of green in the middle of the, like water in the middle of the land, which is not right. Here, of course, also if you know what happens with curves that are not proper powers, you can, so you know what happens with curves that are not proper powers, you can always deduce the proper powers. So the right thing is to look at the proper powers. So let's go back to the proper powers. And the counting, you see the numbers get bigger and bigger. And to see, I just did pictures. So the top picture is, well, black means there's no curves. And when there are curves, the darker the colors, the more curves we have. So anybody see any pattern when I risk it? Curves? Wow. Physicists answer. Good, no, doesn't do it. Somebody else. No, yes. That is a quadratic recruiting. That's the fact. Well, if you look at it, depending on how you look at it, this is a quadratic function. And the interesting thing is almost the quadratic function of the node, really gives you that the counting is quadratic. And also, if you look at a row, especially the last row shows, you see that you start with very few curves. These are very few curves with little intersections. And then we go to the middle, and then there's more and more and more and more curves. So a lot of curves with the mean, some intersection number, and then you start to decrease. Ah, lost my connection.
You're saying there's an exact formula?
For the quadratic, yes. That's it. Well, I prove it with Torn, I prove it with anyway.
What is this like?
No, it's on the nose, not asymptotic. It's like you say that if you look at if you tell me word length L, I tell you the maximum of the intersection you can have is 3 square or 2. I don't remember what it is, but I can tell you exactly. But it's only for the pair terms and the countertorts. And I think that's asymptotic for other, it is asymptotic for other surfaces. Anyway, so let's look at this row. This is the row. All the free homotopy classes that can be represented with the word of A letters, and they are organized by self-intersection now. So the 16 simple ones, we know self-intersection. And of course, you look at it better, we put a histogram, with a height proportional to the number of curves you have there. And you start to see how, it grows in the middle. And so, or more. Did you look at that? This was me? Oh, yeah.
No.
Anyway.
Okay.
So, the other half, growing and growing, what happens when we take more and more, longer and longer, row length, how they are organized. And this was really experimental. So, when I did this in a workshop, the last histogram is workshop 20 letters, and I found out that for the example of my set, and my probability is very vast, but I remember that line has worked with similar problems, considering statistics with some intersection and length is a probability. So I spoke to him, and I said, the distribution of number of curves, by intersection, when you sample by word length, goes to a Gaussian when you take, the word length of infinity. So he answered, I don't think so. So I sent him this picture, and he answered, let's prove it. And, oh, gee. So we did prove it, and basically a Gaussian, you have to normalize in certain way, but for every surface, it only depends. It's not depending really on the topology, deeply only the number of generators. You with a certain mean and standard deviation to constant that gives you the mean and the standard deviation, and there it is. From the world length of infinity, you get closer and closer to a Gaussian. And what you need, or if you are me, you really need somebody who knows probability, because we can think, central limit theorem, and you think, well, he was, counting how many AAs you have in a bunch of words. Yeah, that's central limit theorem. But pairs of things, there's not an easy way, as far as I know, to count. So you have to, it is done, that you need somebody who really knows what they're doing with probability, and that's the plan. And we extended that with the joint sooner we have with Dennis. We extended this result for surfaces, for closed surfaces. It's more or less the same idea. And here is a piece of this that I really like. I was just browsing an old probability book, and they were computed, you have a dents, and you throw a bunch of sticks on the dents, and you count the number of crosses of these sticks, and you throw them, so that uniform probability of pairs of the extremes, where the endpoints of these sticks hit the circle. So they were computing, probabilities and statistics with that, and it turns out that the mean was n squared over 6, where n is the number of sticks. And we get, should have written there, when we have our Euler characteristic is really, really, really large, the constant that you get to multiply alpha to multiply L to get the mean also goes to 1/6. So, very pleasant. Because imagine a surface, with, it's like a polygon with many, many, many sides, it's almost a circle. Especially, when you remove your glasses. So that was great. But then the variance that, as well, we computed the variance before that also goes to the same, it's 1/45. I mean, if you get 1/45, you have to be right, but that's not random. Anyway, so that was statistics. Oh, gee, I went very slow. Sorry. And maybe I'm going to skip a little. Well, let me just say this and I'll skip something else. I like the comparison. I always like to compare the geometric world and the combinatorial world, and what happens. So, still earlier now we proved that, well, when we have L, the word length is large enough, most intersections are close to L squared times a certain constant. And on the other hand, imagine now that you have a very large Euler characteristic. So you have very few intersections. If you fix L, the word length, and you have a very large Euler characteristic, you will have most curves but very few intersections. If you do the same thing, the same game for geometric length, always constant negative curvature, a hyperbolic surface, there's no, up to now, there's not a histogram. I suspect that that is much harder to experiment with that, because we can always put all words up to a certain length in a computer and put all close to the exit up to a certain geometric length. I can do it, but my circle is very small. So yeah, when you fit the L, and I think I said something wrong. If you fix the L, in the case of the geometric case, if you fix the length and make the Euler characteristic very large, you get very few intersections. You have a very large surface, very few intersections. If you fix the length and make the Euler characteristic very large in the combinatorial case, you don't go to zero. You have bunch of intersections. It is a very big difference. There's a lot of things where these two words, it's a mirror, it's slightly distorted, but not in this one. It's very, very different. Okay, so I think keeps disconnecting. And since I have all the machinery to work, I did the same computation, but now I replace, instead of solving the section, we look at hyperbolic length, metric, and this is in the scale of facts. This is some work I did a long time ago with the undergraduate and an emeritus professor. It was like a very, very big age gap. So the idea here, we chose some random words and we compute the geometric length on some metrics. And as you see here, the metrics, what I have there is when you have your funds, you can determine the metric by the length of each of the cards. And here I have the possibilities, the examples I computed. And I'm going to wait and see if somebody asks the question.
It was quite suggestive of the second order.
Yeah, but the thing is, that's one thing. These are going to disappear when you go big. The spikes are going to disappear because they accumulate because there's a big difference between the length of the card. And that was worries that for a second, but they're going to disappear. But there's another remark, which is that I don't see well, but here, one of my length is 10.11 on the top right. And this one in the bottom left is 0.1110. So these are the third figure of numbers. And that's worrisome because the three boundary components of the pair of functions should be the same, but I made a choice. Then it's always said, if you make a choice in math, you pay. So here, by choosing certain generators, it's not reflecting the symmetry that we have in the pair of functions. This is what I explained. But in the limit, in fact, now we know because Goldman, Taylor, and Tioso, they generalize this to much more. Now you have a very general hyperbolic manifold, and you make exactly the same computation. The length, this statistic with the length of all the elements goes to a Gaussian. So this is in fact true. That's what we did years ago. Oh my gosh. Okay. Well, I want to talk two more things about this and then try to go to the Goldman bracket. So I played the same game with now this table is about the pair of counts. I'm counting curves in the pair of counts, which is a very special surface. And again, column is an intersection number, and rows give you the word length. And this is what you get. And you can probably, I don't think you can see the numbers, but when two cells are painted with the same number, they have the when two cells are painted with the same color, they have the same number. So there are these patterns that are not completely explained. I have put a student to work on that, and he did a little something, but never finished. He went to grad school and led the thing. It was a little complicated, so grad students, I can send the table to whoever wants because this needs to be proven. And there's another thing, I always show this because I'm very intrigued. So there's a sequence, the pair of counts, one of the special things it has as a surface is that it has finally many pre-homotopy classes of a given self-intersection. You only have 3 simple curves, you only have 3 curves of self-intersection 1 and 9 curves of self-intersection 2 and so on. So you can count them. That gives you a sequence of integers. I would really like, some way of generating the sequence. Sorry, stop recording. Okay, I have to no defensive, connection lost. So again, anybody interested, here is a sequence, and I'm going to answer the question that everybody asked. Have you tried the cyclopedia of integer sequences? Yes, I did. And I tried to approximate in all the ways that I could, and nothing. That is an interesting sequence that I think should be explained by somebody. And I'm going to finish with a pair of cards, but now, because I listen to Dennis, and he says you have to try not to choose it or be very conscious. So instead of for the pair of cards, we just consider an alphabet that will not make choices when you represent curves with a certain word. So we take the ABC alphabet and we're going to represent it with the shortest word possible. And we play the same game. So it's like you add one relation and one letter. So so here is our word. And I made a table again. So new alphabet, new way of computing word length for a given free homotopy class. And again, row is word length, column with the section number. And here, color do not imply same number, but there's a relation that I'm going to explain in a second. So we look at one of these diagonal-ish organization of rows, and it turns out that they follow quadratic polynomial. So meaning that if I find the polynomial, so in this case I have P of 4 is 6, P of 5 is 18, P of 6 is 38. All the rest of word length, they continue with, quadratic polynomial. And no, this is work Tony Phillips and Kurt McMullen. So we look at all these diagonals and experimentally found that they're all different quadratic polynomials. Here they are. And the diagonals, can be characterized by the difference between self-intersection and word length is constant. And let me explain why. Now we have a clue of this fact, and we know why. So here we have the curve CAB, and again think of it as a ring of letters. And it turns out that if you go around a little more, so instead of CAB, I do C squared, A squared, B squared, I add. Every time I add one letter, I'm adding one self-intersection. So we counted, and if you do this game, well, you get a quadratic, the curve. Sorry, if you organize the classes that follow this pattern by word length, there's a quadratic polynomial that gives you how many you have for each word length, and the self-intersection is constant. So this was very promising. But then what happens if you look at another word? Like it seems like if you have repeated them, remove a letter, remove a self-intersection, we are done. Then not, because well, here when you do that, we're going to see that you lose more self-intersections than you should when you remove one letter. And here is the explanation. Here is when we can remove. So now, up to now, I had a topological surface, there's no metric, and now I'm going to have put a hyperbolic metric, so each boundary component is a puncture. And then here we have a very interesting the curve that I have. So if you look at it, the point is, when can I remove very safely a word and remove one with a section? If you have a curve that is out on the top of the cuff and goes a few times, you can always remove one. So here is the green one. The pink one, if you remove one of the pink loops, you're going to lose more of intersection by removing one letter. So we realized, here, we have my group here, that in fact, the group that we have was not the correct one. sorry. I mean, these two pieces of curve, they correspond to, sorry. Now, doesn't like it, here it is. So these two pieces of curve, the green and the pink, they correspond to the BB. And one is longer than the other. One has to be closer to the cup. And in fact, if instead of the group ABC, you replace A by XY, B and YC, and C and ZX, where X and Y are these, you know, like the seams of the hands, then, and, you know, X now is the, you know, X, Y, and Z are a reflection across these seams, then you have a new writing of your word. You know, we are going to look at the close curve correspond to words on even letters where you have one X, you know, one of each, because, you know, well, the square of each is one, is the identity. So now you need a longer string of two of these. For instance, here I have 5 Z, Y, Z, Y, Z. That tells me this is the outmost thing in the cup, and here I can remove one letter and get, you know, when I remove one letter, I get one of the section less. So you see, sorry, I was a bit confusing, but more or less you push the thing to see who's the outmost loop. And by adding this, by changing a little bit the alphabet, by enlarging the alphabet, you can count the half pieces, which are the one who tells you who's the longest. Okay. And now I'm going to change gears. There's one more thing, you know, when I tried to do my ambitious plan for the talk, I was thinking going from Lefschetz, and I was thinking ideas related to the Lefschetz number, which is what I work in my thesis in dynamics, and I started to talk to Dennis, and he mentioned the Goldman bracket. In fact, the usual joke I tell is that, you know, some women, you know, started the romance with somebody with roses and chocolate, and I started with the Goldman bracket. But it was good. I liked it. So this is a beautiful structure. Okay, I'm going to stay here. So now, again, we have the free homotopy classes on a surface. The surface has an orientation. It's orientable and it has an orientation. And notice that I'm emphasizing it's a set of free homotopy classes. It's not a group. So I do this. So now let's take a vector space. Let's just take linear combinations of elements of this set. And this is going to be our vector space. We're going to define a Lie algebra. So our minds tend to say that, well, if you get a curve and the curve inverse, one is minus the other. No, there's no relation here. The null homotopy group is another element of the basis as the other. So I'll tell you the Goldman bracket. Anybody knows the Goldman bracket here? Oh, really nice. Good. So you're in for a treat. You can, if you were sleeping, you can wake up and just listen to this. So I said that this is a Lie bracket for a set vector space, and then I put Z, so it's a model, but I'm going to define it in two elements of the basis. So you take two curves, here I have my two curves, and you put them so they intersect in transversal double points. And the bracket will have one term for each time these curves cross, for each of the, you know, intersection points. So here is the bracket. So I'm going to go, here I'm looking at first the term corresponds to the green intersection point. And what you do there is you resolve the point, always following the direction of the curve. So same thing with the other, and you put a sign by comparing the two tangents, you know, of the two curves, that they are ordered, you know, light blue, dark blue. You compare this with the orientation of the surface. So I have They've never used specs, but here I use it. So here is a key point is that we are combining these two very familiar operations. One is the intersection, and the other is the loop product. Of course, if you have two homotopy classes, you can multiply like in a space with space, but we go where you can perform that product, and we do it. So what do I have to prove? I didn't say, that when to define this, I start with two classes, the three homotopy classes, and I chose two representatives. And then I did my thinking. I require the representative intersecting transversal double points. But if you choose, this is to be the moral of this talk, if you choose something, you have to be careful. So I have to prove that it doesn't depend on the choice that I made. So this is well defined, in other words. So this, I would sue Steve Jobs with my iPhone, but he's dead, so I can't. So this is well defined. It's Q-symmetric on the nose because I put the sign looking at the order that these elements are. And the interesting thing is also satisfying the Jacobi identity. So this, I know why, can't because it's here. So this is the proof that is well defined, and the idea is, well, you have two pairs of curves, that they are the red and the red are homotopic, and the blue and the blue are homotopic, and you want to prove that the bracket is the same. And well, using transversality arguments, you can find a path. You can deform these two curves simultaneously, so that every time you go to something unusual, like a triple point or a tangency, you traverse it like this. So the coordination one things, you just traverse. So basically, you're going to change the picture of the curve only in a little bit, and I put the three examples there, the possible changes. And in each of the cases, you check, here, I don't know, in this one, when you go over a triple point, you have to check with all directions that, say this point and this point, they give the same bracket and so on. It's just checking. So since, when Dennis told me the bracket, I thought, I like to always to find ways of, finding the minimal intersection number of two classes of curves. And I wonder, well, say I compute the bracket. I mean, I take three homotopy classes, there are signs, so maybe there's cancellation. Is it there or not? So the number of terms, and I should say, the number of terms, counted with multiplicity that the bracket has, the number of terms is not equal to the intersection number. It's always smaller or equal because I can always start with two representatives that intersect in the smallest number of points. So I will have as many terms as the minimal intersection number. But maybe after taking classes and using the signs, things cancel. Well, here shows that things can cancel. Well, I don't know, something happened with my slide, but the idea is if you take these two curves, they are, now in the pair of times, one is A capital B, the other is A capital B. And if you follow the red curve, you will see you do first, well, AA and then B, and then you do the blue curve, pointed maybe. Let's just do one. I really like go around curves, sorry. So this is, let's compute the bracket corresponding to this yellow point. So this is, you go A, and then capital B, and you're back here. And now you have to go around the blue curve. Again, we multiply when we can. So here we do capital B and then A. So the cyclic ring of letters is 3 A's, 2 B's. Now, if you do the green point, you get the same ring. And the signs are opposite, so they cancel. So then, yeah, there's no point of, there's no hope in counting exactly. It's an upper bound. It's a lower bound. the self-intersection number. No, this is here. I mean, one can prove that Goldman did prove that if you have two classes, the bracket is 0, and one of them is simple, one of them has no self-intersection, then the classes are disjoint. So one simple, bracket 0. So here we have, it's a little bit of, well, when the bracket is 0, the equality and when the bracket is 0, one of the terms is simple, the result holds. And many years ago, I proved that, in fact, if one of the terms is simple, the bracket counts intersection. And the idea is, well, you use here, in this case, free products with amalgamation when the curves separate. It's analogous thing when the curve doesn't. And basically, your curve is you go one piece, the other piece, the other piece, and bracket in every term is you insert the curve, the blue curve, the x, between each of every time the curve goes from piece to piece of this decomposition, and there's no cancellation there. So let's see. One thing I can do one place, the other in the other, and I'm going to skip this. And why is it this here? Gee, this is not like. I was not going to speak about. Oh, maybe this. Okay, yeah. Let me just go here. And here is something that gave me a lot of things to think about. So the Goldman bracket almost, gave me my marriage, and a wonderful paper, and I was reading it, and then I start here. In this picture, Goldman says he's computing the bracket of a curve and the same curve with the opposite direction. And then they say locally around the intersection point, self-intersection point of the curve, when you have the two curves, you take two copies of the same curve, you get a picture like this, and there's two terms, and clearly they cancel. From the picture, it's obviously they cancel. So that's it. And those are, famous last words, like from the picture, it's obviously they cancel. Well, it turns out it's not true. First, in fact, I said, why is this true? I cannot see. And I started to just mindlessly put the things in the computer. You make the computer to compute the bracket of x and x bar, or x and x inverse. And it never gives 0. In fact, there's never even cancellation here. So if you compute the bracket, this is the term AB. All the terms look like a commutator. Here is, a self-intersection point divide the class into loops, A times B. So the bracket will be AB. So it will be like the commutator of AB. AB, A bar, B bar, minus BA, B bar, B bar. Oh, this is one term. And terms never cancel with each other. And so that's a conjecture that I can prove. A couple of years ago now, a group of you, why I prove it, but only the case with the bracket is 0. So the bracket of the curve and the curve inverse is 0, then x is simple. And I'm going to do a little switch now for intersection for a second. So going back to the way of describing curves of intersection that I mentioned in the beginning of my talk, when everybody seems to be awake, I can use that to compute the bracket. Again, I can see now the pair of three homotopy classes and get the list of terms. Because if you feel so inclined, you can just do it in my website. There's an app to compute it. And it's really interesting that, the combinatorial work here does work like the geometric one, because we have two homotopy classes, and well, the bracket is you go where they intersect, and there you go, you take the product. In the combinatorial word, what you do is you have two words, and now the combinatorics will tell you pairs of subwords. One word here and one word here. And I just realized I only talk about self-intersection, but intersection of two words works as self-intersection. So pairs of subwords, one in this curve, one in this curve, determine the intersection number of these two classes. So if I have this class here, and here is a subword, that determines my intersection, I'm going to do a cut there in a precise spot. So I cut, but I'm going to cut, I'm not going to cut my finger, I open it up in the precise spot. And the other subword is appear here, and these two are directed, so I'm going to just glue them here, and that will remove the bracket. So cut it and glue it. And that's how I found, that the XX bar is not only false, but it's super, super false in the sense that there's never cancellation. And well, in the beginning, we couldn't prove the XX bar, so we started to study XX cube. And in fact, XX cube counts of intersection, and this was a very combinatorial proof. And I'm going to end, I think I'm going to end here, if I have people still awake. I'm going to tell you nice ways to use, hyperbolic geometry to define the graph. This is for the graph students, okay? It's a nice construction that we can all understand, and it's something, again, that you can take home. You need to have the other thing. So first, I have now here, this is the Poincaré. I have two hyperbolic transformations. One has the blue axis and, labeled by X, and the other has the red axis. And their axes intersect. And I want to find the product. And again, the product is also a hyperbolic transformation. So to find the product, this is the intersection point here, Q, of the two axes. So I'm going to find another point, I call it here QX, that is a distance half the translation length of the intersection point, but I'm going backwards in the direction of X. And on the axis of Y, the red curve, I put a point half the translation length of Y, but in the direction forward.
Your surface downstairs, this theorem.
It will be. Right now, I'm just taking product of two hyperbolic transformation of the Poincaré, and ta-da! The axis of the product is the line that passes through these 2 points that I just defined, and the proof is super simple, because you just write each of the transformations as a rotation, of pi around each of the points, and one is, I don't know, you write Q, and then write Q, and then you make sure the Q's in the middle and cancel, and this is it. Isn't this pretty? Okay. So now I can use this, I can look at this same thing when I have two curves on the surface, I lift them, I lift them based at the intersection point. And you see here is the term of the bracket. If I have my curves and my two curves, and I go to an intersection point, you can think of the product as, well, you start at the point, you run around, say, the blue curve first. When you come back, you turn in the direction of the red, you come back. So you do a factor. So this is a quasi-geodesic. When I leave that, I get the zigzag curve. And that's the axis, it goes in the middle of this zigzag curve. And there's a very nice picture when you look at this. So if I do this, now here I'm in again, back to the Poincaré disk. So here, this is the axis of, the product. This is, one is X and Y, and then here, this quadrilateral, this is Y times X. One is XY minus 1, and the other is YX. when you project this, well, of course, it doesn't need to be projecting there. Here, I just have a made for instance, because when you do these green points and the blue points, you get these torus. There's four curves, there's the two original curves, and there's x, y, which is yx when you project, and then x minus 1. So you can look at this, and it's that. So this quadrilateral appears, or maybe the image of this quadrilateral where we are computing the bracket. And maybe I should end by this. I didn't talk about the proof of Jacobi. I had it in my, I think I did something with my slides, and there is a proof of Jacobi, believe me, and it was really nice, I can say. But here there's another proof, besides the one I didn't say. And the idea is here you have you see, there's the zigzag curve, which is, made of, you can imagine this as made of pieces of blue and pieces of red. And you have a third curve that is going to intersect one of these two curves. So here, well, if you compute the bracket using only geodesics, your new curve is here, is light green, and it's intersect. And when you enter this triangle, there's this lemma, I think it's called Papp's lemma, where if you enter a triangle, you have to come out, from one of the other two sides. So basically, coming out through this side will give you a piece of the bracket, this, well, no, I needed my old proof, but bear with me. I'm trying to organize it. I forgot, how was it? I'm going to look for my good proof. I can end with my good proof of the Jacobi, and then I have to bring that back to my head. Which was, I don't know how I skipped it. Here it is. So we call it the stone algebra. So I'm back. Sorry, this is a very disorganized talk. Now I'm computing the triple bracket. At first, I need to tell you some. Okay, so here I have this picture, the three curves, and this means you get two intersection points of these three curves. So, for instance, here I have P highlighted, P, which is here is intersection of the red and the blue, and here I have T, which is intersection of the green and the red. And again, I'm computing the bracket. This is all to compute the bracket of first red and blue, and bracket this with the green. So I imagine this that I'm going, in a curve along the curve, and when you arrive to one of your points, say P, you have to turn to the other curve, but only for this point. And then you keep going to go, and if you reach the other point, you turn. At some point, you're going to run along the three curves. So this is what this symbol means, like this is all the intersection points of the red pairs of the red and the red and the green and the red and the blue. So now let's do the bracket, which is here. So let's compute the bracket of the red and the blue. Well, this is just meeting the red and the blue. And the picture means all intersection points of red and blue, you do the product. Now, if I bracket this with a green curve, well, you can you can intersect a piece of the red curve, or you can intersect a piece of the blue curve. And again, each picture means go along all the pairs. And then you do the same thing, because we're trying to prove Jacobi with the triple brackets. And now you look at this picture. And of course, here I have red in the middle, And here I have red in the middle, and there are 6 possible pictures, and they're organized by 2. So these 2 are the same, and the sign, well, you check. Look, here I have, this is red and blue. So here I have red, blue, and then I have red, green. So red, blue, and red, green will give me the sign. While here I have red, blue, but I have green, blue, and no blue, green. So I change sign. There's a flip. So these 2 are going to cancel, and so all are going to cancel, and I'm going to finish on the hour. I'm done.